I'm Hlayisi Baloyi, the Applications Engineer at the Gravity Department. My colleagues have spoken about the fine chrome recovery and the ultra fines, and all this they've been talking about a top size that is limited up to 1 millimeter. For many years, the spiral application has been limited to a top size of 1 millimeter, especially in heavy minerals. It's only in light minerals like coal where you find that they can treat up to 3 millimeters. So what's the problem with any sizes that is above 1 millimeter for heavy minerals? It poses separation challenges on spiral models that are built for -1 millimeter. We had to look at developing a model that should be able to cater for sizes that are bigger than 1 millimeter. So with our experience and understanding of transport phenomena on spirals, this enabled us to develop a unique geometry that can handle coarse particles. So beside the 3 millimeters and the 2 millimeters that I have spoken about, what we have seen as well is that in ferrochrome, we have observed inefficiencies even in spirals for particles that are below 1 millimeter. This is largely due to the irregular flat shapes and the high SG that also add into beaching. And if you can look at the pictures there on this slide, you can see the sort of flat shapes on the particles. For what we have seen as well comes to even metal recoveries. We have seen that shaking tables have been the equipment of choice in metal recycling. Metal recycling is generally a growing industry that requires more capacity. So with shaking tables, we know they have got capacity constraints, hence the need for spirals that have got high capacities. And we know in these circuit boards that they have got high metal content. And when you crush this circuit board, they come with top sizes of between 1 to 2 millimeters. And given that they've got metal, then the feed, you find that it got high SG because of the metal content. And that result in beaching if you were to feed this type of feed onto a spiral that is designed for -1 millimeter. There are some other inquiries and other possible applications that pushed us into the development of a spiral that can handle particles in heavy minerals that are larger than 1 millimeter, and also that can handle the irregular flat shaped that I've shown you in previous slides that we encounter in ferrochrome. So we have encountered inquiries in iron ore where the client wanted to treat iron ore with top size of 2 millimeters. We have encountered inquiries of metal recyclers with top size of 3 millimeter on feed. We have encountered inquiries for gold processing with top size of 2 millimeter, illuminate samples with top size of 2 millimeter, and in some other countries as well, like in Zimbabwe, where they are mining alluvial chrome, which is well liberated, but you find that they only take the -1 millimeter and they don't have milling options, so you find that they discard anything that is above 1 millimeter, yet it contains well liberated and recoverable chromite. So these other factors, these are the ones that pushed us into the development of this unique spiral that is intended to treat this type of ores and with these sizes I mentioned. In ferrochrome, we ran a test on this new spiral which we call the SC25, and this spiral was compared with the SC21. The SC21, bear in mind that this is a spiral that is developed specifically for -1 millimeter. So in this case it was used as a sort of a benchmark. So not to say that the SC21, we don't expect it to perform when it comes to 3 millimeter particle. So as you can see on this table, the comparison between the two, you can see that the SC25 achieved almost 3 times mass yield and almost up to 3 times more in terms of metal recovery. And what we observed on this new spiral, which is the SC25, there was no beaching on it, yet on the SC21 we had beaching. By beaching, that's where you have got particles are flowing on the spirals. You find that they slow down, the velocity gets to 0. The SC21 like I said, it's designed for -1 millimeter, so this poor performance here, it wasn't a surprise in this regard. And we have also tested this spiral on -1 millimeter as well. Like I mentioned before, that what we find on this -1 millimeter, we find these irregular flat-shaped particles, and with the high SG, you find that the current spirals or the current models that are applied on this -1 millimeter ferrochrome, you find that the spiral beaches. So hence we trialed these new spirals on a recleaning stage of a ferrochrome section. And as you can see, the cumulative recovery versus cumulative mass yield, you can see that throughout the range, the SE25 curve is above the SE21 throughout the range. And as well, what you can see on these plots, the slag plot versus the metal plot, they are furthest away, which shows that there was high separation efficiency achieved on the SE25 spirals. And some more results. We also took a sample from current spiral plant tailings. So this is ferrochrome slag that had gone through a spiral plant. So we wanted to sort of show if we can enhance some benefit or some recovery benefit onto these tailings. And as you can see from the graph here, the SE25 achieved higher grade at throughout the range compared to the SE21. And on the next plot, you can see as well, when we're looking at the cumulative recovery versus the cumulative mass yield, that the SE25 recovery curve was above the SE21 throughout the range. And we can see as well that the silica curve, the chrominal curve is furthest apart, which implies high separation efficiency achieved on the SE25 compared to the SE21. Some more results as well. We also received a different sample. In this case, it was ferromanganese, -1 millimeter as well. And the ferromanganese as well, in terms of shape and in terms of the SG as well, it's similar to what we experience in ferrochrome. And as you can see as well in these plots, that the SE25 recovery curves was way above the SE21 manganese recovery curve throughout. And the SE25 could also achieve high metal purity as well. And we also looked at other commodities as well, which is chromite, and I've mentioned chromite regarding the alluvial chrome in Zimbabwe. In this case, we tried a hole size range up to 3 millimeters, and as you can see here, we were comparing the SE25 versus the SE21, which is meant for -1 millimeter. And as you can see here, the SE25 shows high chrome separation efficiency than the SE21. And what we found as well was that the SE25 reported lower silica content in the concentrate. We went further in terms of checking what happens if we trial the SE25 on the -1 millimeter in chromite. Here we took a feed sample that was with a top size of 820 microns. And here, this is where you can see that the SE21 is more applicable, because it shows in high chrome separation efficiency than the SE25, which implies that the SE25 in fact is not meant for finer fraction when it comes to chromite, but when it comes, because chromite doesn't have funny shapes that we encountered in the ferrochrome and the ferromanganese. And this also adds that the SE25 might possibly have applications in the -1 millimeter in chromite. Thank you.